Okay, so my name is Joonas Leppänen, and I'm a senior design engineer at ABB System Drives, responsible for the power semiconductors used in our products. And today I'm going to give you a very brief introduction to corrosive environments that these power semiconductors are often exposed to in their applications. I have divided this presentation into few sections. So first of all, I will, in only one single slide, show you what are the effects of corrosive environments in power semiconductors, and I think you already saw this short video that I made about power cycling and thermal cycling related tests, and there I probably showed you a couple of pictures about the packages and how they look. So I don't go into too deep details about those today. But nevertheless, I will give you one very brief slide about what do these failures look like. Then I will describe the impact of humidity, how it affects these power semiconductors, and why it's really important to take this into account, especially with power semiconductors when compared to other microelectronic devices. And finally, I will have a couple of slides about the impact of corrosive gases. So let's jump into, let's jump into the presentation. So first of all, this is a very conventional picture that can happen. Sometimes you have a failure, you don't know what it's caused by, and the destruction looks something like this. By the way, this stuff covering the chips is silicon gel. It's transparent, but you can see that it wrinkles a little bit and bends the light. So that's why all these chips look funny beneath, and that's why actually this explosion that has happened looks so large, because it's also inside the silicon gel. But yeah, this is an open package, very small power semiconductor package. You can have multiple of these chips here, maybe some diodes like these, and another diodes here, and then some MOSFETs here. So very basic functionalities in principle, but on the other hand, because they need to transfer really large currents and really large voltages, meaning the power densities are really large, that's what makes this so difficult. And I'm not going into details about the power densities and so on, because that's covered in my other lectures. Nevertheless, just to remind you that these stands here on the sides are actually the contact pins that are coming out from the package, which can, for example, cause an easy path for the humidity just on the surfaces of them, because of the poor adhesion between the silicon gel and it. But of course, the silicon gel itself is hydrophobic, and it transfers humidity quite easily eventually through. But nevertheless, there are the first kind of failures that can be easily seen can be in these isolation trenches between the copper traces. For example, here, I don't know if you can clearly see it. Actually, this picture is not from the same package, but yeah, just a case example. You can see these copper sulfide dendrites growing there. That's one typical issue that's been around. And what you need to understand here is that the growth rate of this kind of dendrites is highly dependent on the voltage. So, for example, here in this article, they tried to see what's the effect of different voltage levels 50 volts, 500 and 1000 volts, you can clearly see a large difference there. But on the other hand, also humidity plays a huge role there. So 80% relative humidity has barely none when you have low enough voltages. But on the other hand, when you increase the humidity to 93% relative humidity, you start seeing already something at 15 volts even, and then at 500 volts it gets much worse. So just to remind you, these components are typically used on 500 or 1000 volts or even more. So really, we are really typically on somewhere on this region, and also the humidity levels can be really high. Maybe this 93% is a little bit overkill, but it is possible in principle. Of course, you could hermetically try to seal this, but it is not cost-effective solution for these kind of packages. This kind of a package has to cost really not a lot, only few euros or something like that. Yeah, but then on the other hand, you can also have chip level issues. For example, in this article, reference 4, by the way, the references are here on the bottom. I have tried to have them here. Some of them are just internal references, so you don't get to find them, but many of them are from papers. So yeah, there is a possibility for the chip passivation adhesion loss due to the corrosion on the non-stoichiometric nitride films grown by PECVD, for example, here in this article, and that can lead to cracking of the nitride, and then finally the loss of adhesion, and then we have a path again for the humidity to transfer. I will show you briefly a little bit more about this on my next slide, but this is another case that can happen. So just to remind you, there can be issues on both on the package level and also on the chip level. And by the way, this polyimide passivation is the surrounding, this dark area surrounding the chip active region. This active region is this metallic area, and then this maybe a little bit yellowish here on these chips. That region is the passivation region. Yeah. Okay, so let's a little bit talk about the impact of humidity. And first of all, I will briefly show you how the moisture penetrates the package. So yes, as I reminded you, the packages are not hermetic. In principle, you could make them hermetic, but yeah, what would be the cost for hermeticity to achieve it? It's simply not feasible in the most of the applications. And besides, these are like a shelf stuff. So these are not really typically custom-made packages. So these are like you can buy them from the shelf or from any dealer. Maybe not from distributors directly, but yeah, it's a shelf stuff typically. Okay, so moisture penetrates the package. Let's assume that, and you might have this kind of a silicon gel on top of the chips. Sometimes you can have epoxy, which also passes the moisture eventually through. But yeah, in many cases you have silicon gel, and then you have the chips here and the bond wires on top of them, and so on. So the moisture will definitely penetrate through and agglomerate on the surfaces of the chips, and also on the isolation trenches, for example. So practically every surface. And it is typically said that anything above 60% relative humidity is going to be problematic, because it is enough to build up the electrochemical cell when you have more than 3 monolayers of moisture on top of each other, you can have an electrolytic cell then, and that typically happens at around 60% relative humidity. So of course, dependent on the surfaces, whether it's hydrophobic or not. But okay, let's assume now that the moisture has penetrated the package. It takes 1 or 2 days, dependent on the environment, but around 1 to 2 days, for example. And typically, it's considered to be a sort of cumulative effect, in that sense that if the humidity is, for example, during nighttime higher, it will accumulate every night, even though at the daytime there would be dry air. It will not pass, it will not get out there instantaneously like in the air. So if you measure the humidity from the air, you can have really fast drying there, but inside the packages beneath the silicon gel, things are totally different, because it again takes time for the humidity to get out of there. So in a sense, it's considered to be a cumulative effect. Okay, so what happens at the chip level? You might have this kind of a water film forming on top of the chip passivation. By the way, this is a diode package. You have the top electrode here, the anode and the cathode. You have the P-type doping here and the N-type here. And because this is a power semiconductor, typically we have this kind of a field stop N plus typed region on the bottom electrode. So the current passes through the chip. I have not highlighted the whole chip, so this is only really small area of the active area. So I'm now concentrating primarily on this edge region. This green stuff is the passivation film covering the edge termination region, and this metal sort of plugs are the so-called guard rings that are typically surrounding the chip, and the idea is that their purpose is to terminate the electric field towards the chip edge gradually. And you can see this blue dashed line here. It is the depletion region boundary of this PN junction. And with this P-type wells here and these metallic plugs, we can dimension the electric field so that it will terminate towards the edge, and then we can have this kind of a field stop structure here on the edge with a floating metal field plate on top of it. So the idea is that this structure has to be there in order to terminate the electric field, because otherwise there would be exactly or almost the same potential here on the edge as here. So between this point and this point, there can be even 1700 or even 2000 volts difference, and the chip thickness is typically 100 micrometers. So eventually, if there would be this high voltage here, you can calculate what's the electric field. It's really high, and there could be a breakthrough through the edge. And especially because the bottom side of the chip is typically solder, and there can be solder splashes on the edge of the chip here. So definitely this can cause a breakthrough. So that's why we need this kind of a terminating structure, and it has to work there. So if it breaks, there will be a voltage breakthrough somewhere here, and the chip will eventually fail. That's that's the brief story about why we have this structure. Okay, so now when we have this humidity here, eventually it will pass through this passivation film. Of course, if it would be some ceramic material, it will not pass as easily, obviously. But if it's a polymer type, which is very common today, and then of course it's possible to eventually penetrate the passivation and get in contact with these metal guard rings, for example. And then on the other hand, as I described in the first slide, also this there can be a nitride layer on top of these metal guard rings beneath the polymer type passivation and the metallization, and that can obviously also corrode when moisture has penetrated the passivation, and then there will be a loss of adhesion, for example, and you can have a path for the moisture to transport through here towards the area between these guard rings. And because we have a voltage difference always between these guard rings, there will be an electrolysis, of course, and that can cause obviously issues. So what you need to remember here is that the packages are they will eventually, the humidity will penetrate through them, and also the chip passivation is typically a problematic one. But okay, let's first concentrate on a case. I have a literature case published by me and Vesa some time ago this year about a case where we had a glass passivation, and there the problems actually were on top of the passivation rather than beneath. So let's look at that first, and then after that I have another case where we are discussing about problems between these guard rings beneath the passivation. Okay, so first I will briefly describe you how we can generate these kind of problems. So there is this test called high humidity, high temperature, reverse bias, high voltage direct current test. So H3TRB HVDC. Typically just we call it H3TRB test for short. But it is important to remember that whether you are using this high voltage DC or not, because there used to be this kind of older standards like this YEDEC standard. It is a good standard in other ways, but it describes the tests only with low voltage, and that's a really problematic one for power semiconductors where we really have high voltages. So maybe this test was originally made for microelectronics that are not used for high voltages. So eventually the electric fields would be really low. And if you remember the slide where I showed the effect of voltage on this copper sulfide dendrite issue, the same applies here. So that's why we have developed this kind of a test together with the industry. There are plenty of different companies now doing this kind of test with high voltages. And then the purpose of this test is to act. It is really an accelerated light test, to be honest. But on the other hand, typically it is really difficult to calculate what's the actual accelerated factor, and no one really typically calculates it, but it can be in principle done. But it's always component dependent. So the package dependent and chip topology dependent. But it can be used to compare different edge termination topologies. And how it is done. Well, of course, we elevate the temperature level, and we elevate the relative humidity level, and then we use typical voltage levels. So we don't accelerate it by voltage. We just use typical voltage levels in the application. And the test setup can look like this. For example, this is our test setup, and it's just a typical weather chamber, and you have this kind of a computer here, industrial computer that's used to control the test. And about the acceleration factor, yes, there are literature available that you can calculate the acceleration factor, but the problem that I described is that this X here and this EA, the activation energy for the Arrhenius factor, and this Y here for the voltage dependence, they are all unknowns and are chip topology dependent, and that's why it's really difficult to and tedious to come up with this kind of a model. So you would have to do this test at multiple humidity and multiple voltage levels, and even maybe at multiple temperature levels. But to be honest, this is, in my opinion, quite difficult to do. It will take typically multiple batches of tests, and that's why this is often overlooked, and just use this test as a design comparison test, and then avoid the designs that don't pass this kind of a test. Typical test durations are 1200 hours or 1000 hours. It depends on entirely on who does this test, and it's not relevant typically, because typically the good components are really immune to these kind of issues, and it's a sort of either the component fails or it doesn't fail, and of course there are sometimes you can see differences between different type of chips, but typically the result that is wanted from this test is that the components should pass this kind of a test. So okay, we have typically 85% relative humidity, 85 degrees ambient, similarly as in 85-85 test. But then we have this bias voltage, which is often 80% of the maximum blocking voltage. So for example, a typical 1200 volt power semiconductor package, it's 960, and for another 1700 volt package, it's typically 1360 volts, and the gate voltage is always set to 0, because otherwise we wouldn't have this kind of a blocking behavior on the edge termination. And for the failure criteria, there are different means to do this. Some automotive standards state that it should be 5 times the reference leakage current, or in some cases we use this 2 times. Typically ABB uses 2 times. It's just peanuts in my opinion. It can shift a little bit the distribution, the failure statistics distribution, but really it doesn't really matter what's the limit. It has to be reasonable. Just it cannot be 1 ampere or 1 milliampere. It has to be somewhere in the range of tens, or at least less than 100 microamperes or something like that. And with silicon carbide and other wide bandgap semiconductors, it's even lower level. And that's why we use this doubling of the reference. So we always take this reference as a value when we started the test. Shortly after these humidity and temperature conditions have stabilized and we have turned on the bias voltage, then we measure the leakage current and use it as a reference, and then monitor it when it doubles from this initial value. So that's the main idea. And typically we use for each sample a separate reference value, because there is always some variation between samples. Yeah. And the test setup typically in schematic wise looks like this, that we have these DUTs there. These are actually MOSFETs now, and there can be plenty of them. And then we have a current monitoring for each, and then we have this kind of a data acquisition measurement. And in the LabVIEW software, we monitor this data, and when we have an exceedance of this limit, we will try to cut this each of these channels separately nowadays. It's not actually shown here that we have this kind of capability nowadays, because in this early paper that was published a few years ago, we didn't have it, but typically we have this kind of a relays or MOSFETs controlling the circuitry so that we can cut each sample separately off, because eventually they will be in a short circuit if there is a failure. And if we look at what happens to this reverse bias voltage blocking behavior during these tests, is that typically it should be when we start increasing the voltage up to, for example, to 80%, it should be still relatively low. And then at this 1 or close to it, we will have a breakdown. And then the leakage current increases dramatically. And this is the region where we don't want to be. Of course, it will fail if we would be very close to this normally in normal operation. So that's why we use this 80% typically. And typically, actually, there is always even several hundreds of volts margin from the nominal value that's stated in the data sheet. So it doesn't really break down even at the maximum allowed voltage. So really it's somewhere beyond that. There is margin always a little bit. But nevertheless, the green curve here is what it should look like. And then after test, there can be, for example, this kind of a behavior that somewhere at lower voltage level, there will be this kind of a bump, like in this blue curve. And there will be at least a doubling of the reference current. But then the final breakdown will appear here still. In some cases, there are just this kind of a lower breakdown voltage. But there can be also even a combination of these two, this blue and red, so that there would be this kind of a doubling already somewhere, and then there could be even lower breakdown voltage. Depends on what status of the aging these components are. So this is what you have to remember, that this is the first sign of deterioration. But obviously also the leakage current monitoring during the test is always important. But it tells us the leakage current at one certain voltage level, because we cannot have multiple voltage level obviously during the test. So it only gives you a 1 point from this curve. But then with for example, curve tracer measurements, you can measure this kind of a graph before the test and after the test, and then you can compare them. So this is the basic idea on how we can distinguish whether there is a problem already. Any questions to me so far?
Maybe, Jonas, I can have a question what students are thinking. Just concerning the final measurements. So do you have some kind of a recovery time after the test to drive out the moisture, or is it that you just ramp down the test and then you make the, let's say, the curve tracer measurements immediately? Because at least some 85 standards, there are, let's say, criteria that you need to allow the sample to recover if you compare the initial test and the result after the testing. So how that is done in practice?
This is a really good point, and actually we do have really similar procedure than in this 85 test. So typically we put this into an oven for 24 hours, and they should be at least to some extent dry at that time. But obviously they are not 100% dry at that point. But yeah, there are standards for that, and I think for this JEDEC standard there was a separate one even. I don't remember what was the number of that, but it is really similar to 85 test in principle. You could do this also on room temperature, but you would have to wait a little bit longer time. I don't remember, was it 2 days or how much was it? But yeah, there are a couple of different standards to do that, and we typically follow some of them. Yeah, that's
okay,
a good.
Thanks,
that's a really good comment.
Maybe just another comment here for this, so more for the students, so that now the thing which Jonas has now emphasized here is the difference between being able to let's say calculate quantitatively the lifetime and then comparing, let's say, different things like designs or materials. So also this we can consider more in the category of highly accelerated tests, where there are lots of challenges related to lifetime estimation, but still there's a huge usefulness of the test, so that, for example, you can develop new solutions, new structures, and also compare vendors. So I would assume, Jonas, that is also really important for you to utilize this test to, let's say, see that how different vendors, their solutions, how they would, let's say, survive in your applications.
Yes, exactly. That's the main idea here, and even the suppliers are using these to compare their who are really making these chips. They are really comparing different chip generations and different chip topologies and improving their components. And sometimes we see things, we buy components from different vendors, and we see things that they don't see because they don't have the large amount of information from different chip topologies, and what chip topologies are really more robust than the others, and what should be avoided. So that's the main reason why this is really common, this kind of a test nowadays.
Yes, Jonas, there's a question in the chat. So Scott is asking, what is the point of trying it before the final measurement? That seems like it wouldn't correspond to when components are used in products.
Oh, yes, that's a good point. The thing is that we of course monitor the leakage current during the test. That's for sure. And the level, we know that the level of the leakage current is highly dependent on the relative humidity and the ambient temperature. We acknowledge this during the test, and that's why we have this online leakage monitoring during the test, and we have this reference value that is really measured at these, sorry, something happened, at these test conditions, and then on the other hand, this kind of a curve tracer measurements, you cannot do these measurements at high humidity. It's a separate test setup. It has to be always done at the room temperature and ambient conditions. So it is not possible to do it at the chamber. Yes, we could build up a setup that we could do it here already in the chamber, but would it give us anything new? Because you cannot study the component itself at high humidity after the test. Let me show you in the next few slides, what I mean, why we cannot study it at high humidity. You might get the idea why it is really simply impossible to further analyze it at that high humidity and keep the humidity there. So yeah, it's like a car crash. We see the damage that has already happened there. We don't see the actual phenomena. That's true. And unless someone gets me a better alternative to do this, this is how we try to do it. That we look at the what has happened rather than what is happening. So it's really simply impossible to do that kind of a measurement, but this is something that can be obviously developed further, and I think it would be actually quite nice and interesting to see in situ what's going on there, even with the humidity. But to my knowledge, there are not equipment that are capable of this kind of analysis.
Yeah, so the let's say in situ measurements are giving the, let's say, temporary values for that specific voltage or whatever is used, and then this ex situ afterwards, they are the permanent changes. So as you will see in the next slide, so what is really happening, which is not recovering. So again, let's say referring back to our how testing these limits. So we have the operational limits when something starts electrically failing, so that the circuitry is not functioning anymore as it should be, but it's not. There's no, let's say, permanent damage yet, or then we exceed the destruction limits like we see here, so that then after certain let's say failure mechanism has propagated far enough, then the smoke comes out and then it's not working anymore. Okay, but Jonas, please continue. All students, please ask questions. It's because we have now today time, so I'm not sure about Jonas how much time you have, but basically, so please be active so that you get maximum out of this, because this kind of nicely concludes our testing part of the course.
Yes, please go ahead if you have anything, and if you can, Vesa, look into the chat. I cannot see them now.
Yes, I will follow the chat and I will stop you if there's a question.
Yes. Okay, let's proceed. Let's start with one kind of a failure that we have seen here. This is from a published paper. It got out in August this year, and this is an interesting study because this in this case we had a glass passivation, and we were thinking that nothing penetrates this glass, and all the problems should be on top of the passivation. So let's look. We had two different chip technologies, technology B and A, and all of the A-type technologies failed. This A-type was a glass passivation, and B-type was a polyamide-based polymer passivation, and we had both lower power and higher power chips. Well, all of these were high power if you think about it, 50 kilowatts and 60 kilowatts. Yeah, but all of this A technology failed, and they were glass passivated, and only one single chip failed from this B type. We didn't investigate that too thoroughly, this one single failure, but we were concentrating on efforts on this A technology, why it doesn't withstand this test at all. So what we found out, this is a leakage characteristic measurement from one sample. Before the test, it was like this, and now after the test, the leakage current was really high, and we decided to go into lock-in thermography microscope where we can see the thermal hotspots. Logithermography is a method which is, in principle, it's a fancy thermal camera microscope, but it's actually based on pulsing the voltage source, so that the software will integrate multiple of pictures, thermal pictures, based on these excitations that comes from the pulsating the voltage, and when it's integrated thousands or hundreds of times, you can reduce the noise level of the thermal measurement, and then you get only this kind of a hotspots that are really the hotspots there. It's a really nice method, and it seems to work quite nicely. And then we were able to pinpoint the hotspot into the chip edge termination region. This is, by the way, a diode chip. And then when we looked with the SEM, by the way, these two pictures were taken by Vesa. Thanks for Vesa for that. But nevertheless, we saw that there are these kind of a tree-like structures there, all over the edge termination region. And in some places, we could see that the morphology had already changed locally quite dramatically. So they were really burning or breakthrough through these structures. But in some places, we saw this kind of smaller tree-like structures that had just started growing. And we could see them growing from both ends of the edge termination, so from both polarities. And then in some cases where we had this kind of a really large burn marks, we could see also cracks there. And one of the hotspots were localized here into this region. And then we made a focused ion beam cross section, and finally made a lamella out of it and looked at it in the scanning transmission electron microscope, and saw that, okay, instead of growing on top of the glass, it's growing actually just beneath the surface. This is actually the glass surface, and this part here on top of it, it's actually kind of a supporting structure that was made when we made this kind of a lamella sample. So it's not part of the original structure, so the surface is here. And we can see that it's growing inside there. And the other thing is that it doesn't have any kind of a crystallinity. So it's amorphous similarly as the glass. While based on the literature, the dendrites that I showed you in the first slide, they are typically growing on top of the material, and they are actually either polycrystalline or maybe even sometimes even partially single crystalline. But amorphous is something that's not known by the literature, and also it shouldn't grow inside the glass. So this was something else. Then we made a bright field STEM image and made an EDX analysis, and then we saw that, okay, because this is a lead-based glass. This is, by the way, interesting that it's still allowed to use lead-based glass in the passivation material. It's actually an exemption from the Aero HS, and it can be still used in these applications. Maybe the content is so low, and because the chips are so small, it's not that's why it's not banned probably. And also in some applications there are not alternatives. But nevertheless, it's still there. We can clearly see that in this material, in this darker region, that's the tree-like structure. It's the lead has depleted there, so there is no lead, and we don't know where it goes. It doesn't go into the glass, the glass looks the same in every other direction, and we can clearly see that the oxygen content here in this tree-like structure is higher than normally. By the way, if you want to look at this article, you can Google this. It's available for free actually. It's an open access article in microelectronics reliability. And then there are more information about this case from there. For example, there are even better EDX results there available. But nevertheless, we saw that the lead has somehow depleted. And we tried to look from the literature what can happen. So what is this glass made of? So it's silica plus this lead oxide, PbO typically, and then there can be some other materials like alumina. But nevertheless, somehow this lead has depleted, and we tried to form this kind of a Pourbaix diagram. If you have gone through this Principles of Material Sciences course, you might remember these Pourbaix diagrams there. But the idea is that with Pourbaix diagram, we can explain what kind of reactions can occur and at what kind of pH level it can occur. And then if you think about it again, this whole edge termination region from here to here to the edge of the chip is a kind of a electrolytic cell when moisture is there and voltage is there. So basically, at the anode end, this lead oxide can dissolve into lead hydroxides, for example, this lead hydroxide 4+, or even a lead hydroxide plus. And then finally, these can dissolve into lead 2+, for example. Nevertheless, all of these compounds are it's possible to dissolve them into water. And what makes this issue even more interesting is that because they bear this kind of a tree-like structure, and it is believed that this issue is related to this kind of a water treeing phenomena that's seen in for years already in high voltage transmission cable insulations. There they have even much higher electric fields, and it's similar to partial discharge. That's where this electrical treeing is also common. So this is really a similar phenomena that the water will agglomerate into when it agglomerates into the surface, and we have a high electric field there. It can form this kind of a tree-like structure, this water film, rather than just this kind of a larger area. And it is believed that that's why it's only a local phenomena, and that's why it's locally dissolving in these tree-like structures rather than all over the glass. But nevertheless, in the anode, we can consider that there could be this kind of a dissolving of the other material, and then here there could be this lead hydroxide 3- on the cathode side, and we have this kind of a tree-like structure, and this tree-like structure, when it doesn't have this lead oxide, is less well, actually it's also maybe not 100% less insulating, but also the ions there in these tree-like water flakes, they are also more conductive than the glass, and that's why there will be a breakthrough sometime during the test. But on the other hand, also we consider that this area where the lead has dissolved is less insulating than the original glass, and that will cause the breakdown also. But yeah, nevertheless, this is one interesting topic, and this was something new. We didn't anticipate this kind of a phenomena, and then I was really surprised to see this kind of an issue. I was really hoping that I would get this kind of dendrites growing directly on top of the glass, but really this was a surprise to us that there is something totally different ongoing. But yeah, this work has been published in Microelectronics Reliability, so feel free to look into that. Okay, so then another topic, aluminum corrosion issue. First of all, we have this kind of a different tests, and we have failure statistics out of them. This is how we see can compare the lifetime from different techniques. But actually, in all of these tests, we had the same technique, except in this one batch we had different voltage level. So that's why it looks at that it's accelerated a little bit more. But okay, what we saw there. First of all, we realized that again the leakage characteristics had deteriorated dramatically. Then we used this information and did this lock-in thermography and found out that okay, there is a hotspot in 2 of the corners of the chip, of one of the chips. And then we made a SEM image and overlaid this lit image on top of it. You can see here is the hotspot. This red yellowish region here is actually from the lit image. And then beneath that there is this SEM image. And when you zoom in to this hotspot region, you can see that there is a crack in the polyimide passivation film. By the way, these are now all of these are now with polyimide passivation, so polymer-like passivation. And then you can see clearly that there is, when we take a FIB cross section and look into it with the SEM image, that there is a corrosion in the guard ring here and deformation in the field plate, and it's clearly in quite bad shape. And then when we look into a little bit deeper, if we go into top view image and remove the passivation by oxygen plasma etching, and then look into it, and we see that between these 2 guard rings, for example, one of the guard rings is really badly corroded, and we can see that the aluminum has formed this kind of a bridging structure beneath these 2 aluminum guard rings. You can see it here in the top view EDX, that aluminum is here where it shouldn't be. And when we look in this, when we make a FIB image out of it, we can see this clearly that it grows on top of the passivation, well, on top of the silicon nitride structure, and the silicon nitride structure is really badly damaged. It's even cracked in some places, like here, and actually here. But yeah, that's really clear that there is a bridging corrosion structure forming here. So what can explain this? First of all, we can form this kind of a Fourier diagram, and then we can try to explain this idea that at the cathode side, well, actually at the both sides, even without the voltage, this aluminum hydroxide 3 would form on both of the surfaces. And actually we believe that this happens already in our tests before we start biasing the voltage. So we start only biasing the voltage only shortly after we have reached the conditions. So maybe already some of the humidity has penetrated the package and the chip at that time, and then we start having this aluminum hydroxide there already. But nevertheless, it will eventually form also even with the voltage on the surfaces. But nevertheless, this aluminum hydroxide 3, it can dissolve at this cathode side, meaning at this higher pH level, into aluminum hydroxide 4-, which is, according to literature, stable throughout the pH range, maybe because it takes longer time for it to react. So it is believed that it can migrate through this isolation barrier to the other end, and then finally finally agglomerate here and form again this aluminum hydroxide 3. But then on the other hand, at this anode side, aluminum can directly also dissolve into aluminum 3+, but it is believed that it's not as stable as this aluminum hydroxide 4, and it's believed that it cannot transport to the other edge. It will eventually react and then form this aluminum hydroxide 3, but it is believed that it plays a role also in the formation of this pileup. And because we can see damage already at the both ends, so we can see in this cathode side, we can see damage in the surface of the aluminum, except it's quite local. But on the other hand, it's also seen in this anode side that there is large damage also. So we think that both of these reactions will occur and cause this kind of a pileup of the structure, and finally leading to a breakthrough. And that's actually what explains this deterioration of the leakage characteristics. Yeah, any questions?
Maybe again a comment from my side. So I think this is also a very nice example of this kind of a concurrent reliability engineering, where you really need to have the understanding on several different, let's say, directions. So I would say that this is needs a quite fundamental electrochemistry. Of course, we don't need to go into, let's say, modeling of electrolytes or anything like that. But anyway, to know the basics of electrochemistry, so how the voltage affects on the pH, what kind of ions are moving, where they are moving, how they can form, and so on. And on the other side, then you need to understand the, let's say, the functionality and the testing. So you need to have the, let's say, principles of the power electronics also. So that's the reason that quite often you need to have different a team to analyze these things. So of course, Jonas has here done all the analysis part, but then a little bit of help on the microstructural analysis. I mean, the SEM work, FIB work, PM work is then coming from our side. So that is, let's say, just to point out that these are difficult things. Even the standards test might seem quite straightforward, but then when you really want to understand what is happening there, why the components or test devices behave as they do, then you need to go on deep into details, because of course, if you would like to improve this, prevent or slow down, then obviously you need to, let's say, develop something, either new structures or new materials or combination of those. Okay, yes. Any questions from student side or comment, Jonas, from my comment?
Yeah, as I think Vesa pointed out this quite clearly, that it's really tedious work to do this, and there are not so many groups in the world that can really or are willing to invest time really on this kind of an analysis. But yeah, these are really difficult issues in that sense that it's really hard to explain and then get rid of them. One way would be to get rid of aluminum. That's one way. Get rid of aluminum and decrease the electric fields here. That's one way of handling this issue. But yeah. Okay, so if no questions at this point, let's jump into the corrosive gases. Let's remind what are the conventional corrosive gas tests. So first of all, there are different standards available. For example, this IEC standard, which describes this kind of test method for corrosive gas test with relatively low concentrations. So 100 ppb, 200 ppb, NO2, and so on. But then on the other hand, if you look at the standards for the environmental classification, these three conditions from this ISA standard is really common that's allowed for the components. For example, 50 ppb of H2S. And now when you look at these, it's only 100, so it's only double. And the test duration is 30 days. I don't know if it's written here somewhere, but nevertheless, it's 30 days typically. And the temperature is only 30 degrees. That's already another question, that is it enough? And also the humidity level is quite low. If you remember that for this H2S, we had seen that the difference between 80 to 93% was already quite significant. So is this even high enough? So that's another question. But nevertheless, it must be noted that these tests with this low concentrations, this low temperatures, and this low humidity levels cannot really show us that whether this component will fulfill 20 years lifetime at these D3 conditions. And that's actually a common mistake that's seen in the field of this industry, that people start doing tests with these low concentrations and then they claim that their product is capable of fulfilling 20 years at G3 conditions. And that's not at all true. So these test standards are really outdated and cannot really reproduce what we see in the field. And there is, in the next slide, there is evidence to support that a little bit. So I reminded you already a couple of times about this copper sulfide dendrite growth, what we can see in these isolation trenches between the copper traces in the package. And this is really common when in applications such as mining, wastewater, pulp and paper industries, and marine industries, and so on. So whenever you are close to these kind of applications, you really can see these kind of effects really fast in half a year or 1 year or something like that. So really, this is really a difficult issue. Somehow it needs to be solved for these kind of applications. There are, of course, I will show you a little bit about also the solutions later on. But yeah, what happens here? So moisture penetrates again the package, and then it agglomerates into the surfaces, and we have electrolytic cell here between these traces, in the isolation trench, and then copper can grow into this kind of a dendrite when hydrogen sulfide is there. And why it actually is so problematic is that the electric fields can be really large. So typically the isolation trench thickness or the width is around 1 millimeter. And if we have 1700 volt device, for example, it can be even 0.17 megavolts per centimeter, for example, as an electric field. So it's really large already. Yeah. And then in literature, there has been description about the reactions that can occur. And I have been trying to draw them into this Purbe diagram. Sorry, I didn't remember to put the reference for this Purbe diagram here, but in principle, you can just Google it. It's Purbe diagram of hydrogen sulfide and copper. And it is not currently known clearly how this reaction works here. There have been trials to explain it a little bit. So, for example, maybe this reaction A occurs first, so the hydrogen sulfide will dissolve into hydrogen and S2 minus first, and then there will be one of the reactions. Actually, in these B reactions, B reaction it actually is two reactions at the same time. So first of all, it's this dissolving of copper into copper 2 plus or copper plus. Maybe copper 2 plus is more common. Plus electrons, and it happens here on the other edge, and then this S2 minus can migrate towards this copper 2 plus ion or copper plus ion, and then react with it to form copper 2s or copper S. So copper sulfide in principle. So this is how it's best explained at the moment, but it's not 100% sure. Is this reaction correct, or has there been a misinterpretation of the possible reactions? But at least this Purbe diagram should give us a nice overview what can happen, and this is one likely explanation. The only question remains that this reaction for this S2 minus to form, it is not in the stability region of water, so which are actually shown here with these green lines. So that's a question that will it really occur or will it not occur? But somehow there needs to be some ion that will react with, or some compound that will react with the copper and form this copper sulfide, because that's actually the end product that has been seen there. Any questions at this point? Okay. So what can be done to test this kind of issue? You remember this H3 TRB test? You can come up with a test that's almost the same, but except it will have this hydrogen sulfide in really high concentrations there also. Some people are also using sulfur dioxide, but it seems to be less reactive with this copper in this kind of a case. So this is actually the best alternative at the moment. And the concentrations are typically from 25 to 50 ppm and 85 for the temperature and humidity. And then the voltage is 80% of the maximum DC voltage. It's actually the same, just the same parameter that was in the H3 here, but it's now just written a little bit different way. And then during the test, typically the voltages are like this, that they are from this DC plus plate to DC minus, but it depends on who does the test. Some people are just doing it a little bit differently, but this is one way of doing it. And then you remember this picture that there is a high dependent on voltage and high dependent of relative humidity also. So definitely this is justified that it has to be really high temperature and humidity level, and also the voltage level. And then it was realized in one paper that typically the mass gain when it's measured, when the mass gain is measured with this kind of a copper or silver coupon, how much will it gain mass during the test? That's a really common way to measure the corrosion effect during the test or during the use operation in the application. It was realized that at 25 ppm, the mass gain will not anymore rise, so it saturates already. So that's the question why that is asked, that should we actually do it at 50 or 25 ppm. So in principle, you could do it at 25. Maybe you don't get failures that fast, but in 1 month or 20 days test, you should see something. This is actually from 10th day for 50 ppm. You can see clearly already something. Some of them are already almost as long as here, but it's not as dense as here after 20 days at 25 ppm. But nevertheless, it's really enough to have 25 ppm for this kind of a test in principle. But then also for this test, people have been trying to calculate what's the actual acceleration to this ISA standard G3 class here. So for this kind of a test, you can obviously do it with these copper and silver coupons. The idea is that you have limits in this ISA standard for this corrosion gain for this, for this mass gain for these coupons for both copper and silver described in the standard. For G3 conditions, and then you just compare them. It's actually 2000 angstroms per month, and now they had in this test 5,000. It's 504,000. So it's 250 times more than here. So the acceleration factor is 2050, which actually stands for, I think, 20 years after 20 days test. So that's already something. So with these coupons, you can estimate a little bit what's the acceleration factor here, and it's highly standardized. So in that sense, it's good. But will it tell us the whole story? Because these are always bare metal plates. So how about the situation inside the silicon gel of the component? Because there surely has to be some kind of a time constant for the gases and the moisture to penetrate. We know that for the moisture, it is typically less than 2 days, but for the gases, is it the same, especially in high humidity? So that's something that's been studied recently a lot, and there are discussions that whether we should have this kind of a two-phase test, that we would have a sort of this kind of a dry phase and then the wet phase. So in the dry phase, the the gases could penetrate, and then we introduce the humidity, and the gases would be already there inside the package, and then only the moisture would have to penetrate, because in literature it is seen that moisture can actually prohibit this gas penetration, because typically gases are then dissolved into this moisture, and then they would be surrounded by water molecules, and then it would be less easy for them to diffuse through the porous gel. But that's a discussion that's ongoing in the field, and then let's see if within a few years we might have a little bit different kind of a test type to describe these issues. But nevertheless, this is probably the best that's available at the moment, and it can reproduce this kind of issues, at least in the worst packages. Any questions to this H2S H3 TRB test? You can write them down even as we go forward. We can come back to here if you want to comment. Okay, so then there is this final one. I'm having this kind of a trial how to protect these coppers. So how to cover these copper traces with something that would protect them from the corrosion. So first trial that has been used for many years is nickel. But the problem with nickel is that there will be always a gap somewhere. Somewhere here, for example, in the close to the interface between the isolation substrate and the copper plate. And you can see that after this test, there will be a bridging dendrite at some locations, but at some locations there wouldn't be. So this is already totally burnt structure, so you don't anymore see the dendrite even here. It will do some protection. There will be not so many dendrites there, but there will be some, and they will be in these locations where this protection film hasn't been totally covering the gap here. And there you can see in the EDX analysis that there is copper here migrating already, and there is sulfur there also. So there is copper sulfide definitely here. And nickel is here protecting. So that's one trial that hasn't worked so well. But on the other hand, I don't have here now material to show, but some people are trying to have this kind of a sacrificial material in the gel already, so that the gases wouldn't penetrate, especially the hydrogen sulfide wouldn't penetrate the gel at all, so that they would have this kind of sacrificial material where there would be some copper particles inside this sacrificial material, and it would consume all the gas, at least the large proportion of the gas, and by reacting with the gas, and it would never get into the copper surfaces. And that seems to work quite nicely in principle, but there are also some questions on that material. Yeah. Any questions now? Because this was my last slide. Very brief introduction to what kind of problems we have and what kind of tests we have available and what kind of problems we can have there.
Okay, thanks, Jonas. Your brief introduction took almost the whole lecture time, which is fine. No problem with that one, because I think you extremely nicely covered all those points which were also included in my slides. So for the students, if you just go through, of course, you have these Jonas' slides in the My Courses page, but also some of my slides. And there, for example, you can see a little bit more details on the, let's say, the weight increase in the copper coupons and the actual flowing mixed gas corrosion test, how the, let's say, chamber looks like and these things. But the main things came here via the examples, that what is the purpose, what is these tests are good for, and where you need to be, let's say, cautious when you are using these tests for lifetime estimations or this kind of thing. And maybe the most important thing was here to really emphasize the need to understand the failure mechanisms, because otherwise you cannot explain, let's say, what Jonas mentioned, this small difference in something. So it might be a small difference in the gas concentration, it might be a small difference in your actual test sample, it might be the difference in the relative humidity or something like that. And then you end up in having, let's say, completely different numerical results, and then you cannot explain them if you cannot analyze really properly the mechanisms.
Yes.
Maybe while the students are thinking for the final questions, one additional point which I would like to highlight is that in the beginning of your presentation, you mentioned that you have seen that the 60% relative humidity could be the critical one. And now last lecture, we discussed about this classification of environmental conditions. And there this, let's say, time of wetness was defined as 80% of relative humidity when the temperature is above 0. So this just highlights that these kind of things, if you have these rule of thumbs or even standards, they are not always valid. So it's dependent on what kind of mechanisms there are. So this 80% might be a nice average for all possible electronic products which are used in hot and humid conditions. But clearly, for example, if you have these kind of devices where, for example, the voltages are extremely high, then it might be that there would be some other critical limit than 80% or 95% or 60% or whatever. So again, coming back to this statement that reliability is far from exact science.
Yes, exactly. Exactly. And on the other hand, I think this 60% is just that in theory it is possible to have electrolysis there. I'm not saying that at this point we would do any tests. So definitely I would always do this kind of testing at 85%. It's really far beyond this 60%. And if you can get a component that would be immune to all these phenomena in these tests, you would have really good reliability in respect to environmental impurities.
Yeah, and another comment from my side is that it was, of course, nice to see that even if you have kind of hermetic structures like in the glass passivation, it still not means that you are immune to humidity effects. So I think that is also good to keep in mind. And then maybe one question from my side to Jonas, that we have in the lectures discussed quite much about moisture penetration and absorption to epoxy-based materials, but nothing on the silicone polymer. So can you say something about if you compare these IGBT modules, which are, let's say, epoxy molded versus silicone coated, if you think it only from the moisture penetration point of view and exclude the effects of let's say, impurities, is there some clear difference, or is one of the materials outperforming the others?
As far as I have understood, typically it takes a little bit longer for the epoxies to pass the moisture, but definitely they will also transfer the moisture through eventually. And we can see this in humidity tests also. So also there, the chips needs to be robust enough to protect them. So you cannot use the epoxy as a any kind of a protection there for the moisture. For corrosive gases, the story can be a little bit different.
Yeah,
because because how the epoxy takes this moisture in and how it will then most likely decelerate the penetration of the gases if it's there. So in that sense, epoxy could protect a little bit from the gases otherwise, but for the moisture itself, it only makes a little bit longer. It only takes a little bit longer for moisture to penetrate the whole package then.
Yeah, the point which the reason why I brought it up is of course silicon is a little bit specific material for, let's say, power modules as well as MEMS components, but epoxy molded components you can find everywhere. That was just a point to highlight that there are similarities between all organic materials, but also some differences, and depending on the application, you need to use different solutions. But in IGBT modules, basically, you can utilize both.
Yes.
Yeah. Okay, I'm just checking my notes. Is there something else which I wrote on the paper? So maybe one very minor comment for those students who are also taking the sustainable electronics. You mentioned this lead hand. Of course, it sounds a little bit strange at 2021 that we still have lead in our components, even it was prohibited at 2006, so how it's 15 years ago. But it is also a question of leaching. So lead was banned mainly or the main usage of lead was in solders, where in solder materials it's very easy to do the lead to leach or dissolve into the groundwater and so on. But in glasses, it is kind of more bound. And now we saw today that okay, may need a very high voltage to get kind of dissolved from there. Even we kind of finally couldn't figure out where it went. But that's also maybe one reason, in addition to that there are not that good options or solutions, but also maybe it's not that let's say harmful for the environment because it's at least dissolving much more slowly.